Welcome to Almost Here, Round the Corner Future Technology podcasts with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech Podcast. My guest today, it's a recent doctorate, Dr. Joost Huizinga. He's at the University of Wyoming, and his research is into artificial neural networks. So, Joost, how you doing?
Very well.
Yeah. So tell me about your research. What are you working on within neural networks?
So what I'm trying to do within neural networks is I'm trying to make these neural networks more robust and, in a sense, a little bit more, intelligent by making them structurally more similar to the human brain.
I've seen basic neural networks. You have an input layer of nodes, then you have like a hidden layer in the middle or multiple hidden layers, and then you have an output layer. And I see like each layer is connected to the other layers. But what is it like in the human brain, and how is it different from what people have traditionally made as a neural network?
Yeah, so the traditional neural networks that you're talking about are what's called fully connected neural networks, and they generally have this large number of inputs, these hidden layers with large number of neurons, and then the outputs. And what you do is when you train them, what will happen is that you just give the network a large amount of data, maybe a lot of images, and then you train the network to classify those images according to different categories. In the end, that network will have learned to recognize these images. But if you then start to look at the network itself, what you will notice is that it has kind of scattered this information about these images all throughout the network. As in, dogs can be in all kinds of different places, and houses can use the first, the 306th, the 1047th neuron. So it's these neural networks, when you just train them and let the learning algorithms take over, tend to just distribute the information throughout the entire network. This is kind of in contrast to how the human brain works, so we have specific areas for different functions. For example, we have a visual cortex specifically structured to process visual information. We have a motor cortex specifically structured to allow us to move. And even within the motor cortex, you will find there are specific areas for your hands, for your legs, for your neck. Basically, every single muscle has or muscle group has a different area within that cortex. So it's very much, the natural brain is very much structurally organized, whereas our artificial neural networks generally are not structurally organized.
Well, so what do you think happens in the brain? Do you think that areas get trained up, or they're segmented somehow so that each area that works on a special processing, visual cortex, etc., it's the training of that neural network stays in that area, and I guess it gets better and better at it, but it doesn't migrate all over the whole brain.
Exactly, yeah.
Oh, okay. So what would you do artificially? Would you string together a whole bunch of narrow neural networks together but keep them segmented to emulate this, or what would you do?
So, well, we basically asked the question is why are natural neural networks, why is the human brain structurally organized? And there are a couple of different factors that play a role, but one is basically it has no choice. So the rough structure of our brain is determined by our DNA. Basically, it's determined by evolution. But there are just physical constraints where, all the connections need to fit in a skull. So if you want to have a fully connected neural network within the brain, you would have to connect every single neuron within the brain to every other neuron in the brain. And if you would do that, you would need a much larger brain. It simply wouldn't fit within the skull. In addition, every single one of those connections that are made within the natural brain, it needs to be built. You need all the proteins and building blocks to actually build those connections. And you need to maintain those connections. So there are these costs associated with the connections within our brains, within natural brains. So that is the exact thing that we did in our experiments, where the goal is very much not to pre-build the network, but to have an algorithm built a network for us, is to have an evolutionary algorithm build the network, and then in addition to optimizing for just performance, we're also optimizing for these connection costs. So reduce the number of connections and reduce the length of connections. And as a result, by optimizing for reducing the length of connections, these networks that we build also become modular as a result and also start to functionally specialize, simply because that is the most efficient structure if you need to optimize for connection length.
So what does it look like? I mean, if you look at each neural network as like a circle, do you have circles connected together, so different neural networks that connect to other neural networks in some kind of pattern, or what? How can you give like a visual idea of what this might look like?
Yeah, so that's exactly right. So the idea of a module here is basically just a group of highly connected nodes, highly connected neurons. So within this group, you'll see many connections, but then from this group to other groups, you see far fewer connections. And those fewer connections hopefully convey the more important information. For example, if you have a module for recognizing a particular sound, then the output of that module will simply be, I've recognized this sound or not. But within that module, it can do all kinds of processing to recognize a sound or recognize a dog or do something like that.
So what's an example that you've worked on where you've used an algorithm to build a specialized neural network, and what happened?
So I guess the most interesting project where I've used these techniques was on a hexapod robot. So a robot with 6 legs, and kind of in contrast to a lot of previous work. So in previous work, what usually is done with these robots is you give it one task. For example, run as far as possible, or maybe jump, or maybe turn. What we did in this particular task was to have in this particular experiment, we had 6 different tasks that needed to be optimized. So this particular robot had to move forward, move backward, turn left, turn right, jump and crouch, which are basically some atomic behaviors you might, if you want to remote control the robot, you might want to have in this remote control. And the usual technique is to simply create a separate neural network for each of these behaviors and train a separate neural network for each of these behaviors. What we did is we simply took a single neural network and then applied this selection for fewer connections, and then selected for more modular structures. And that makes the tasks much easier to learn all these different tasks, because the network can localize different functionality within that network. And what's interesting about it is also that, so I described these different tasks to you, and one kind of obvious way to make this network modular is to just say, okay, we're going to have a forward module, a backward module, a turn left module, a turn right module, a jump module, and a crouch module. But maybe something you would decide as a human. However, it turns out that if you let this evolutionary process, this automatic machine learning process take over, it actually finds a different decomposition that works much better. In this particular case, the decomposition, it's a little bit hard to interpret these networks, but for one of the networks seemed to have basically one part dedicated to deciding which task it needed to perform, and then another part of the network decided to create the pattern that is needed for locomotion. So a regular pattern that allows us to move its legs into a rhythm so it can move forward. And then the other module of the network would basically modulate that signal to either create a movement that would walk forward, or create a movement that would walk backward, or create a movement that would turn in either direction.
Right. So again, how did it break it up itself? Did it combine the jump and crouch module, or what could you tell that it did? How did it combine the elements together differently?
So it did not create a jump and crouch module at all. It's so one important part of doing a locomotion task is the central pattern generator, just creating a pattern that's allowed for the motion, because walking is effectively just a repeated motion over and over. You lift up your leg and you put it down. You lift up your leg, you put it down. You lift up your leg, you put it down. And it turns out that creating that motion, creating that repeated pattern, that in itself required a separate module. And then the behaviors were basically all aggregated into a single module that could modulate this overall pattern into all these different behaviors.
So that's what the network did on its own. It created the mechanics of walking, and then all the other behaviors were just a manifestation of the different flavors of the mechanics of walking.
Yeah, exactly. So, and that's one example of why I believe this research is so interesting, is that it allows us. So currently, what we're doing is we're hand designing these networks, and we are making use of these structural principles. For example, one of the most successful neural networks for image recognition are convolutional neural networks. And convolutional neural networks have these small filters which process a local part of an image, which are effectively modules, and then they build up this hierarchy of these modules. And there's a lot of research into optimizing these architectures and trying to make them as best as possible using our human intuitions. And I think this was a very good example of how our human intuitions may not always be right. And as such, automated processes, automated algorithms that can design these networks for us may actually find architectures that work much better than the architectures that we design as humans.
It makes sense. I mean, it would help you think differently about a problem. You know, like you said, our first instinct may be to break it down into these behaviors, but the machine found a different way to do it, which makes a lot of sense.
Yeah.
Was the machine's results better than handcrafting this and forcing it to do it the way that we want to do it, with each behavior separate?
Yes, or at least when I tried to do it myself. So I actually forced the network to have these separate modules, and that worked much worse than having the algorithm figure out the structure on its own.
Huh. Have you tried adding arbitrary rules in and seeing how the network reacts to create different circumstances?
What do you mean with arbitrary rules?
I don't know. Let's say that a right turn could only be accomplished, or you couldn't make right turns at all, or a right turn can only be accomplished if a jump came right after. You know, did you kind of like mess with the network and push at it and see what it comes up with under, constraints, various constraints that either make sense or don't make sense?
I have not. I have tried to just see if you could actually do this remote control task and kind of move this robot around, and that works. I have not really put any constraints on the network. So the idea of moving forward, so this was, one level. These were the basic components of the task, moving forward, turning left. The overall goal was to have a robot that maybe could actually try to simulate a natural process. So we wanted to simulate a predator-prey process where it might be able to try to collect food, but whenever it saw a predator, it would have to run away as fast as possible or otherwise avoid it.
Okay.
And that would be basically this hierarchical structure. So that's another structure that you find in the human brain, and often that doesn't automatically appear when you just train neural networks, is this hierarchy of tasks. And so we wanted to try to see if our technique can also produce hierarchical networks, where maybe it's this lower level modules that can do the moving forward, moving backward, turning left, turning right, and then higher level modules that may be able to detect food, detect predators, and switch between either collecting food or running away.
Yeah, like a robot mouse or a robot cockroach or something.
Yeah.
Did you do that? Did you get that far? Or is that still in the near future?
That is still in the near future. We did some experiments, but we currently ran out of computational time to actually finish the experiment. So the robots were only halfway in learning all these tasks. So they hadn't, the robot hadn't really learned to do all of the tasks yet. So we're still working on that. But that's one. Yeah.
Yeah, I guess going back before with constraints, let's say you had a robot that worked in a mine and it was, trained to go pick up rocks or something. And then something falls and crushes one of the optics, or, one of the wheels it runs on breaks off. now the robot, it sounds like it would be useful if the robot would change how it's set up to adapt to the new conditions if it was damaged or if conditions changed. Let's say it navigated by sight and then it also navigated by feel or by distance or something, and all of a sudden it couldn't see, or if something else happened, or something broke on it. This sounds like it may be useful for something like that because the system could evolve around problems,
Yeah, and this is actually something that was not done by myself, but that was done by my advisor. And so the main problem with having evolution figure out a new structure is that evolution is not really a fast process. It isn't a fast process in nature, and it's also not really a fast process within our computers. So what they did was they created a behavioral repertoire. They created all kinds of different ways of behaving in advance. So even before the robots would be deployed in the field, they tried different behaviors where the robot had to, move with all 6 legs, but then behaviors where the robot had to move with one of its legs disabled, and then the robot had to move with one of its legs off the ground, and then with 2 of its legs off the ground, and 3 and 4 and 5, and then try to move without any of its legs touching the ground. And with that behavioral repertoire, because it had to learn to move in so many different ways, when they then damaged the robot in the field, so actually broke off one of its legs and then let it learn again, it was able to very quickly go through all these different behaviors that it had learned previously and find a behavior that would very quickly, within minutes, allow it to walk again, even though it suddenly lost a leg.
Okay. So it was able to adapt around that and still maneuver?
Yes. Yeah. It was able to very quickly figure out a way of moving that wouldn't actually use that broken leg, and thus it would be able to then go forward again and just continue on its way.
Well, can you give listeners a sense of, you said this evolutionary behavior or training a neural network takes time. I know it takes a lot of data and it takes time. So how long did it take for you to train the jumping, crouching, turning robot your way versus the machine's way?
What do you mean, your way versus the machine's way?
Oh, yeah, the way that you first came up with each skill separately, and then you said you let the machine kind of figure it out, and the machine segmented it differently into walking, and then all the behaviors of walking. That's what I mean by your way and the machine's way.
Yeah, so one thing I should clarify about my way is that after I divided the network into these chunks, I did still use an evolutionary algorithm to actually then try to learn to walk. And in general, my way just didn't work at all. So I ran it for probably a week and it didn't really learn. Whereas with having the algorithm itself figure out its own structure also took about a week of computation time, but it was actually able to learn these behaviors.
Oh, it was a whole week. Okay.
Yeah, I'd say roughly about a week that it ran on a single computer, and then the entire experiment was replicated on a supercomputer.
Okay.
So yeah,
in a real, how would you get this to the point where a robot could react within seconds or milliseconds to something happening to it, or is that just so far in the future that it's just impossible for right now?
No, it's definitely not so far in the future. So what you do is you make plastic neural networks. That is, neural networks that can update its own weights while it's running. So evolution is very good at figuring out the architecture of the network, but it's not really good at determining the weights of the network. And that's very similar, once again, as with the human brain, where evolution has determined the rough structure of your brain, but it doesn't determine every single weight within your brain. And that is impossible. We have about 20,000 coding genes, and we have about 420 trillion connections. So instead, the connections learn during our lifetime. We learn to walk during our lifetime, and we get feedback. And that is also what I want to do with my research going forward, is have these networks be plastic, have these weights being able to update themselves based on the feedback it gets from the environment. And so then you get this interesting interaction between the evolutionary process and then the within lifetime learning process, where the evolutionary process tries to construct these networks which are really good at learning. And then when you have these networks that are really good at learning, now you actually can have these networks adapt very quickly to damage or unexpected circumstances during their lifetime.
It must amaze you, it amazes me now that I think about it, how fast the human brain can adapt to changing situations. But what do you think makes up for that huge difference in speed?
I think our really fast reaction times come mostly from experience. As in, when we are suddenly in an unexpected situation, we don't completely relearn really quickly on the spot. In fact, learning new tasks, like maybe learning how to snowboard if you've never snowboarded before, actually takes quite a bit of time, even for humans. But when we get into an unexpected situation where we have to react quickly, I think we rely mostly on things we learned during our lifetime. And this is things like just playing. So as I said, with the fast adapting robots that my advisor trained on, all these different behaviors like learning to use different numbers of legs or only walk on one leg or two legs, that's kind of what we do, especially as children. We play, we may walk around, hop around on one leg for no apparent reason. We just call it playing, except that when you later on break a leg, you immediately have some behavior that you know that you can immediately use to say, well, I know how I can move around with one leg or with one leg injured. So I think most of our ability to adapt comes from basically our past experience.
Okay. Yeah, I just wondered because, again, you made me think of how can we make a network respond extremely quickly. So I guess we'll have to see. Some, nitty-gritty questions about neural networks. This may be getting too detailed, but if you have a certain set of, I've heard there are black boxes, the hidden layers of a neural network. Do you have any insight into what's going on? Let's say, I don't know, I have a neural network that wants to, see if a picture is a cat, and I put in all these features on the front end. What's happening inside the hidden layers to the features? Are they recombining in new ways and then being optimized, or what do you think's going on?
So it's generally really hard to actually see exactly how these neural networks work, but especially with the image recognition networks, the rough structure is usually that it starts by, very much once again like the human visual cortex, it starts by detecting very small elements of the picture. So it starts by detecting the edges within the image, or roughly that a certain area is maybe blue or red or green. And then you have these low-level features like these edges and these blobs, and they can combine into, two edges may make a corner. And then several corners together may make a square. And then that square may eventually make a picture frame. And eventually you can basically combine all these lower level features. Maybe you can detect an eye if you have several curves. And then you can combine two eyes and a mouth, eventually into actually a face. So that's the general way that these image processing networks process information. Though currently there's a lot of research into trying to figure out exactly what they are doing, in a sense that as you get to higher and higher and higher level features, you can get these weird neurons that respond to maybe cats and cars for some reason, or mountains and divers that combine this information. So for the lower level features, it's generally always the same. It's just these edge detectors and then maybe these corner detectors. And then for the higher level features, things can become pretty weird, and you have to really study a network before you know what exactly it is doing.
Well, it sounds like the network can teach you associations you never would have thought about before. Like yours taught you, okay, well, we can break this problem of the robot down into walking, and then all the ways you can walk instead of forward, backward, side, etc. So it sounds like that would happen, and it's cool. The network teaches you back as you teach it, and you kind of iterate towards a solution.
Yeah, exactly. And I think also that it is kind of the future of AI, where currently we are hand designing the architectures and then trying to let it learn. And I think the future of AI is very much in having AI figure out its own structures and basically having AI figure out how it's supposed to learn. And I think that AI can eventually figure out much better ways of learning and also of solving certain problems that we currently have with our neural networks.
Well, what are some examples where you've seen, maybe in your reading or in your personal experience, where you've seen an AI network come up with something that no one's ever thought of, a new combination, a new way of doing stuff? Do you have any examples of what you've seen that you're like, wow, that's crazy?
So there are a couple of different examples. One thing that I thought was pretty funny so in the work that I referenced earlier, where you had this robot that had to walk on 6 legs, 5 legs, 4 legs, 3 legs, 1 leg, and then 0 legs. And you think, wait, okay, walking without legs, that's not going to be possible.
Right.
What the network figured out to do was basically just flip the robot upside down and then walk backwards on its knees so that none of its legs were touching the ground. I thought that was a really cool, clever solution to this problem of you're not allowed to use any of your legs in order to walk.
That's amazing. Yeah, that's really amazing. Any other examples that were really cool?
I'm trying to remember. I know that working with these evolutionary algorithms can be somewhat difficult, and you have to make your code very robust, where in an experiment by a colleague of mine, the AI eventually, rather than actually solving the task, managed to hack the program itself. It managed to overwrite some memory, including its own fitness value, to give itself infinite fitness. So it was no longer solving the task.
Really?
It just hacked the program itself because of a bug that was in the code.
Whoa, that's kind of scary.
Yeah, and I think that's also why this idea of interpretability, this idea of being able to figure out what a network is doing is so important. So another example is from fooling networks, where so if you teach a network to distinguish, for example, dogs and cats, it will be able to tell you whether a picture is a dog or a cat. But if you give it a picture that's completely different, let's say you give it a picture of a space shuttle, now it's really unknown what the network will do with this new network. And as a human, what you want the network to say is basically, hey, you taught me cats and dogs, I have no clue what this is. But what happens in reality is that this network will be really confident maybe that this space shuttle is a dog, because all you ever taught it to do was draw this line. And so it's really good at classifying in this line between cats and dogs. But as you go farther away from that line, farther away from that decision boundary, you get into other things that I've never seen before, maybe TV static or abstract art, it may very confidently classify it as one of these classes, even though it's never seen it before, and it should not have been that confident. And that's, I think, for example, if you think about self-driving cars, using these networks to inform self-driving cars. You can teach it in the streets and to recognize humans and other cars, but I know one example where a network recognizes a black-yellow pattern as a school bus. And if you have a black-yellow pattern next to the highway and suddenly the network thinks that there is a school bus on the road that it has to stop for, that may create these very unsafe situations. So I think it's really important for AI to go forward, to indeed be able to figure out how AI is doing things and making sure that also in the areas where we haven't trained the network, that it gives us answers we expect and not confidently says that it's something completely different for something it has never seen before.
Well, are there systems where you have a governing classifier type AI, and depending on the situation or the object, it'll delegate the figuring out to one or more networks?
You could build such a system.
Okay, I just wondered. I mean, maybe that's, I don't know, maybe that's a solution.
Well,
what have you?
Yeah. The problem is that you need to be sure that the classifier is accurately classifying the object, and that's kind of the problem. Is in the neural networks are very good in recognizing things that look like the training data it has seen. But what we wanted to do for training data are things that it has never seen before and also doesn't have a frame of reference. It doesn't even look like anything it's seen before. what you wanted to do is say, hey, I've never seen this before. Maybe I should be careful because this is something that I don't know how to handle. But instead, the networks we currently are training generally are just very confident that it's something they've seen before and will act accordingly, even though they probably shouldn't.
I guess, is there any sense in training a network where it recognizes dog, cat, or other, and then if it just says other, that's sent off to like another network that would try to classify it, then another and another, like a waterfall or cascade type thing?
Yeah. So you need to do that. The problem is that the network will recognize other by the number of examples you put into other. And that means that everything that you didn't train it on may still be classified as cat, dog, or possibly other. So it's definitely better than just training a network to classify something as cat and dog, but it doesn't necessarily solve the problem.
So what do you see as the near future of your research, and what do you see the field as trying to conquer in the near future? What do you think the improvements will be in the next few years?
So I think on the short term, what you'll notice is that these techniques that can automatically build neural networks will result in, I guess, small increments in things we already use. So small improvements in vision recognition systems or speech recognition systems, or maybe it finally pushes the self-driving car really to be on the road. I think in the long term, what it allows us is to have these really general AI systems where you can give it literally any task. You can say, I want you to control this robot, and it can figure out how to do that. I want you to learn natural language, human language, and it can figure out how to do that. I want you to drive this car, and it can figure out how to do that. I want you to fly the space shuttle, and it can figure out how to do it. I think that is eventually what this technique will enable us to do, is to basically have this much more general AI which can learn and structure itself to completely new problems that it has never seen before, rather than the specialist AI that we currently have, which can do one task but not anything else. And if you want to do anything else, you construct a new network.
Well, does the brain seem to be a marketplace of dozens or hundreds of different specialized AI modules? How does the brain do it?
So the human brain is surprisingly general. As in, it is structured in such a way that different parts of your brain will specialize. But also well known, if you, for example, lose vision, those parts of your brain may now become dedicated to different tasks, maybe increasing your sense of hearing. So I think the brain is very much structured in a way that evolution has created something that's really good at learning different tasks. And I think that's exactly what we can do with these automated finding the structure of neural networks, is find the structure of neural networks that are really good at learning new tasks. Thus, you have maybe this general network that can then learn a lot of new and different tasks without having to redesign it. I think the human brain, at least partly, is built in a very similar way, where the reason that it learns this specialized task is because of what it is connected to. But if it's suddenly connected to something different, for example, because you can become blind or deaf, then these same neurons can now take up a different task. And I think that our neural networks we should try to make neural networks that have the same capability.
Makes sense. Well, very good. So what's on the agenda for you for the next 6 months or a year? Where specifically are you going to be taking your research?
So currently, I'm very much thinking about the idea of meta-learning. So the idea of learning to learn. In our specific case, it will be indeed finding these architectures that are really good at then learning different kind of tasks. So finding neural networks that are really good at learning, and then trying to apply that to problem domains like different either robotics tasks or maybe driving tasks, or even just playing video games, trying to figure out how to play different video games and very quickly learn different video games.
Okay. I guess chess and Go have already been taken up by the champions, so you have to figure out other ones, you know?
Yes, and from a computer's perspective, chess and Go are still relatively simple because they are these well-structured domains. And as you go into the more and more complex, first of all, more and more complex video games, and then into the real world, the action spaces become much bigger. The different scenarios that you may encounter become much bigger. And so I think there's still quite a bit of work to do in that area to make AI be able to adapt to all these different kinds of situations it may find itself into.
Yeah, I've heard of AI playing like Breakout or simple games, but I haven't heard it playing like Counter-Strike or these real complicated games where people run around and shoot each other and stuff. That would be, I guess, maybe the next step if AI can play something like that and be a master.
I think the state of the art currently is probably OpenAI's AI that can play Dota.
Can play who?
Dota. It's this kind of this strategy game. It's a 5v5 strategy game where each player has its hero and then, has to defeat the throne of the other team. And so these 5 players have to work together. They can walk around this map. They have all kinds of different abilities. And the OpenAI company is currently making a lot of progress towards having an AI that can actually play this game, which is much higher dimensional than, for example, something like Go, as in you can go anywhere on the map at any time. And you have to consider the actions of all your teammates and the actions of all your enemies at all times. So I think we are definitely moving there.
Well, very good. Well, Joost, thank you so much for your time. What's a good way for listeners to find out more about your research and maybe contact you for collaboration or questions or anything?
So I would go to www.evolvingai.org.
Okay, very good. Evolvingai.org.
That's the Evolving Artificial Intelligence Laboratory from the University of Wyoming. And there you can find all of my research and all of the research of my fellow PhD students.
Excellent. Joost, thank you for coming on the call. I really appreciate it.
Thank you for inviting me.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.